Yeah, it's very weird. I don't think it does. So then this one. It's not a binary. Now there are people who say, no, it has something to do let's talk
So I'm Mohammed Chanderian from Arman National Lab. I used to be there a long time ago. To make my friends at Arman from Ohio State University, and I'm very jet lagged because I just arrived from India, so it's 11 and a half hours time. Please excuse me. The speaker is my colleague Fengyuan from Ohio State. He's going to talk about zero LANL-SkyrmionWorkshop formation and Epitaxial.
Thank you. And first, I'd like to thank the organizer for inviting this workshop. So, my title is about this high intermediate Skyrmion system. But in the end of the talk, we'll talk about our preliminary result on the outside bilayer Skyrmion system as well. So these are my students and my collaborators, and recently we started collaborating with FeGe on those beachwater and the oxide Skyrmion systems. And this work was mainly supported by FeGe and the project work on our site. So here's a quick outline. So give a very brief introduction to the Skyrmions and for a while, and then we'll do some lunch. And then I'll talk about our technique in growing these syndromes. We use alpha splattering, and the characterization, structural characterization of these materials by XRD, by PEM, etc. And I'll focus on the topological Hall measurement on these systems and get a fixed diagram for Skyrmions and then the outside system, very important results. So this is the Skyrmion picture. We have seen a lot, and it's together the total interaction of the exchange and DMI. So I don't need to say much here. So about this B20 phase materials. So the earlier work was done by synchrotron. You can see this the hexagonal symmetry, and also done by Lawrence TM, mainly from Dokuro's group. And these are all on either iron germanium or manganese silicide, etc. So these are the prototypical materials that shows that can harbor Skyrmion information. And later on, well, mostly my work is about the electric transport. So I've seen this picture this morning. So basically, you have Skyrmions in this material system. You pass a charge current, and then the electrons, when they go through the Skyrmion particle, they're going to experience this emergent electromagnetic field, which is going to be deflected and cause this holological Hall effect. But also, the reaction, effect of that is the Skyrmion Hall effect, which we have heard from, actually this morning, I was going to hear, and Eric this morning, we're going to hear from Jeff FeGe also later this afternoon. Our focus is mostly on the topological Hall effect. So, this indicates that Skyrmions can be controlled or manipulated by a very low current density. That's a major draw for the Skyrmions. And this can define potential applications in low energy memory or logic applications. So since I'm focusing on the topological Hall effect, I'm going to cite two of the many references on this topic. This is a work from Johns Hopkins on iron germanium films. And what you see is this black line is the first quadrant of the Hall measurement. And then if you subtract the ordinary Hall effect, which is linear, and then the anomalous Hall effect, you can extract this topological Hall resistivity. And this shows the two different temperature on the 60 nanometer films. And that's basically the approach we used to study the Skyrmions. Another one is a couple of years ago from the first group on these patent iron germanium films. And then they also studied the topological, well, this is the raw Hall effect. They measured Hall signals at different tilt angles, and there's a very interesting discrete behavior in those systems. So B20, this is a table of B20 Skyrmion materials. Iron germanium has the highest carrier temperature, about 280 Kelvin, and the Skyrmion size is relatively large among this class of materials. It's about 70 nanometer, but it can be as low as 3 nanometer for the manganese germanium. So it really can go down very low, but a drawback of this system is that the TC is still low, so there are efforts that try to increase that TC to the room temperature. So, if we can, well, a couple efforts. One is TC to be about room temperature. The other one is if we can stabilize Skyrmions at a zero or low magnetic field. So that's what this this part is what this talk is about. So we grow the iron germanium films using this technique called ultra-high vacuum off-axis sputtering. So we developed the techniques for growth of oxide materials, which now this also work for the intermetallic system. So these are the growth parameters. So I just want to point out that the growth window for pure phase B20 material is rather narrow. So the sweet spot for our system is about 290 degrees C for the substrate temperature, relatively low for epitaxial growth. If you just go slightly above, 25 degrees above, you're going to see the germanium phase separate out. So you're going to have a mixture phase, which is, of course, not going to be good. If it's a little too cold, 25 degrees lower, you're going to start to see this B35 phase iron germanium formation, which is not what we want for Skyrmions. So we're going to, you just use this narrow temperature window to grow high quality epitaxial films of iron germanium. So this is a large window XRD scan. So we can see that there's no other peaks except this iron germanium 111 that shows this is indeed a pure phase. And also here we show 3 different kind of thicknesses for the films from 36 nanometer to 65 to 100. And this is the B20 iron germanium. So to characterize the surface smoothness or roughness, so we did this small angle X-ray reflectometry measurement. And so we can see wiggles that roughly the refraction of the total film thickness. And this shows the phi scan. Okay, so to verify this is indeed epitaxial between iron germanium B20 lattice and the diamond structure of the silicon 111. So we measure the silicon 400 peak as well as the iron germanium 22200. So you can see there's a 6-fold versus 3-fold symmetry. So to understand the epitaxial relationship, so these are the unit cells of silicon, which is diamond, and the B20 iron germanium. So if we look at the 111 surface of the silicon, this is what you get. You call it hexagonal or triangular. So on top of that, if you lay the iron germanium 111, so you don't directly map on top. You need to rotate it by 30 degrees. And then it turns out these lattice constant match very well within 0.5% if you counter this, take into consideration of this 30-degree rotation. That's why this peak is, well, it's in between of these two. That means we do have a twinning of the iron germanium film. So we also did the TEM. So this is just the scanning transmission electron microscope, microscopy imaging. So what you see here, this is iron germanium, and then this is silicon, right? So in between, we do have something like a 1.5 nanometer transition period, which we believe is even at 290 degrees C, we're going to form some of the intermetallic, right? So like silicium. So that's what this transition layer is about. And then on the top, you'll see this structure, which I zoom in. You can see that you have this not very, not perpendicular arrangement like you expect from cubic. This is due to that if you view this B20 phase lattice from the 110 direction, which is what this is for, and then you have this about 70 degrees tilt of these two sets of these parallelograms. And that's what we see here, that you can match this expected structure with the lattice. So we have pretty high quality film, those from XRD and from the TEM. So now let's do a Hall measurement. So we just pattern this into a standard Hall bar structure, and the Hall bars are not that small, so it's like 0.5 millimeter wide and 0.5 millimeter long. And we use the 40 Tesla BPMS to measure the Hall measurement at various temperatures. So here is an example of the total Hall resistivity, okay, in the unit of nano-centimeter at a 5,000. So this is for 36 nanometers. So you see this this behavior. So this behavior we can actually divide it into 3 regions. Those are due to the 3 contributions to the Hall resistivity. The first one is this linear portion at high field. Well, this is from the ordinary Hall effect, and R naught, it's typically 1 over NE. And the second one is this middle region, this transition, which is due to this anomalous Hall effect, which should follow the magnetic hysteresis, and by the way, this is outer plane measurement, of course, for the Hall measurement. And we expect this to be proportional to the magnetization. Right? I'm going to look at more data about the hysteresis later. And also, the third one is in the middle. This one cannot be attributed to the anomalous Hall effect. And we're going to explain this is the topological Hall signal that we call it rho TH. So, to look at that middle region, right? So we first compare this Hall hysteresis with the magnetization hysteresis measured by squid magnetometer. What you see here, this is the typical out-of-plane magnetic hysteresis with almost zero coercivity. Okay, so the red is going from positive field to negative field, and blue is the other direction. What's different, what's special about this group is because of this topological Hall effect, the Hall signal reverses before it even reaches zero field. So that's the signature of the top of the Hall signal. And then on the way back, it does the same thing. So this is what we focus on, and our goal is to extract that part. So to subtract the ordinary Hall effect, we just take the high field slope, such as from 3 to 6 Tesla, and we just subtract this linear background. And that's what we get. So we have this. The question is, how can we subtract the anomalous Hall signal so we can obtain this topological Hall resistivity? Well, the anomalous Hall resistivity is typically in this form, and this RS is the anomalous Hall coefficient. It could be due to two contributions and depends on the magnetic resistance. The rho XX is the longitudinal resistivity as in the circumference field. So the first term, the quadratic term, is due to the scattering independent contribution, and the second linear term is due to the skew scattering. So we measure the MR data. It has a pretty small magnetic field dependence, and the MR is typically of the order of 0.5% up to 7 Tesla. So it has essentially doesn't depend on the MR. So to determine which mechanism is dominating in this material system, so we plot the log rho A anomalous Hall versus the log rho XX. Basically, we want to get this. This is the data we take at 4 Tesla, at which all the anomalous Hall eventually saturated. And then at different temperature, we plot this. We got a slope of 2.3. So we believe that the scattering independent contribution dominates this anomalous Hall coefficient. So we use this. So we use this as our mechanism. So that's what we put it here. To extract this parameter B, so we plot this rho xy over h, right, versus rho xx squared ms over h. So that should be a linear term. So the slope gives us the b. So that's how we obtain this b. So after extracting this, we can subtract the ordinary Hall here, and then subtract the anomalous Hall effect, this one, and then we'll obtain this topological Hall resistivity. Then for the next few slides, we're going to focus on this topological Hall resistivity. So here we show at 5 Kelvin data, 3 films after subtracting the ordinary anomalous Hall contributions. So here we see that when we go down the field from high field, it switches around here and comes down here and doing like that. So how do we understand this? So we're going to, well, in the next slide, we'll explain this. Let me first show you the high field data. The high temperature data, 250 Kelvin. When you go from 5 Kelvin to 250, the magnitude of the topological Hall resistivity increases from just under 100 nano-ohm centimeter to close to 1,000. So it increases with temperature. This is, has been observed in other E20 systems as well. So we plot this rho TH versus temperature for the 3 films. And this is, remember, this is the log scale. So it increases by about an order magnitude for these 3 films. And we notice that the magnitude of the topological Hall resistivity is close to 1,000 nano-ohm centimeter. This is about 6 times larger than the previously reported iron germanium samples, and I believe it's still the largest reported to date. So somehow, even though iron germanium has 70 nanometer Skyrmion size, but it has the largest topological Hall resistivity. So this is material dependent. Next, let's look at the hysteresis loop. So now we want to find the remnant topological Hall resistivity, because that is the indication of the Skyrmion phase, we believe, at 0 field. Okay, you need to polarize that, and then initialize it, and then you bring down the field to 0, and that's what you get at 0 field. So we're going to define the squareness, Okay, that's typically done in the magnetic hysteresis loop in other systems. So we take this zero field value of the rho TH divided by the maximum, the peak, and then we got the squareness. So the maximum is 1, of course, and the highest we got is at 5 Kelvin, and the value is as high as 78%. So that indicates at 5 Kelvin, when you initialize it and you bring down to 0, you still have 78% of the Skyrmion phase if you relate that Pavlov sensitivity to Skyrmion formation. You can look at the temperature dependence. As we go up the temperature, the Pavlov sensitivity decreases. But even at 200 Kelvin, the 36 nanometer still has something like 30%, which is still a substantial amount of Skyrmions. And so this is the visual result of this work. So now this is what we try to map the phase. Okay, where in the field versus temperature axis, we want to map out where the Skyrmions can be found, as indicated by the Pavlov sensitivity. So these are the 3 films. Okay, so if you look at the 100 nanometer, so this color bar indicates the magnitude of the Pavlov sensitivity, as high as close to 1,000. That's what happens around purity temperature, right? Between around 250 Kelvin. And then the magnitude decreases, but still we have a pretty clear Skyrmion formation around here. And the field, on the field axis, it extends to beyond 1 Tesla, okay, depending on how you define the color plot. So this is where the Skyrmions exist. When we go down the thickness, the range of this Skyrmion phase, as indicated by the Pavlov resistivity, expands somewhat to about close to 2 Tesla for the 36 nanometers. So that's what the phase diagram looks like. If we zoom in into this 2-dimensional plot, you can just look at the zero field line, as indicated by this yellow dashed line. So we have a pretty substantial magnitude of the Pavlov resistivity. That's kind of correlates to remnant Pavlov effect. So we believe we still have a sizable zero field Skyrmion formation, particularly at low temperature, but it exists at all temperatures. So that's the B20 phase ion germanium. So the downside of this material system is its low TC. Right? So far we have not found above room temperature Skyrmions in that system, although there are a lot of efforts trying to get up the purity temperature. Then we look at another system that we have heard a lot about, is this metallic multilayers, very thin layers with ferromagnet and then heavy metal, non-magnetic metal. This is interface-driven Skyrmion formation. This material system has very high TCs, right, because the pure temperature is what, 1,000 K. So that is clearly desirable for technological applications. So here I just show the 2 recent results about the Skyrmion formation. There are many other results as well. I would say as compared to the size of Skyrmion in this system is still relatively large, although there are a lot of progress trying to shrink that. We want to see if we can realize this similar structure in the oxide system. And there are certain potential benefits, as I will explain. So recently, I believe this is last year, Dr. group published this work about the oxide bilayer system. Okay? And that is the strontium glutamate with strontium iriate, both perovskite structure, and they are all very thin, a few unit cell thickness. So the main result of this work is that it harbors Skyrmion formation. Okay, the evidence for the Skyrmion formation is through the Pavlov measurement. So these are all very thin films. So when the strontium glutamate is a ferromagnetic oxide. Okay, its TC is somewhat around 160 Kelvin, still low. And strontium iriate is a non-magnetic provide the interfacial DM interaction coupled with the exchange interaction inside the strong loosening. So what you see here, for example, around 80 Kelvin, for example, this blip is an indication of the top-on Hall because you cannot explain that with ordinary Hall or a normal Hall. This can only be explained by the top-on Hall effect. In fact, these are all top-on Hall effects. So inspired this, actually, he brought this to our attention, saying, well, let's try that, and because we have other ferromagnetic oxide that we can play with that can potentially bring up the TC and also control the Skyrmion side, etc. So the motivation of this material system is, in that paper, it claims that in this system, the Skyrmion side is of the order of 10 nanometer. So it has much smaller Skyrmion size. And this is because the DM interaction strength, the T, can be a few times, 10 times larger than what you would find in the metallic multilayer system. So here we go. So we first try to grow individual single layers, let's say strontium loosening on strontium titanate substrate. And we see this XRD, that is the SROP, and those are the Lavi oscillations indicating high uniformity of the film. And then we grow strontium iridate, also thicker, and we saw a similar thing, and that's the SIO. Then we put them together, we see both peaks, and with the beating of the Lavi oscillation peaks. And here we see the bare substrate of STO, and we put down 18 nanometer SRO, and here we still see the terraces, so we have a pretty smooth steps. All right, so we also did the TEM, scanning transmission electron microscope, microscopy. So what you see here is this is the strontium titanate substrate, and we have a unit cell thickness of strontium loosening, and then a couple unit cells of strontium iridate. And this is similar to what Okura's paper reported. And okay, so here I said that. So now let's measure the Hall effect at various temperatures. So we patterned the hallmark structure, and we started from 5 Kelvin. So we sweep the magnetic field. You expect it's the typical anomalous Hall behavior. So from high field, and then it switches with a relatively large coercivity. And then we come back, just come back like this. Then when you increase temperature, you still have this behavior, but coercivity reduces significantly. Then at 40 Kelvin, the Q3 loop collapse. So basically the two merge together. When you go to 50 Kelvin, and then something interesting happens. And you keep going up, you see this. I'm going to zoom in to this central region. So what we see here is, this is 10 times smaller the range as compared to this, even larger, more so. So at 40 Kelvin, it collapsed. At 50 Kelvin, it shows this reversal before reaching the zero field. So this is contrary to this, well, opposite to this, but it's similar to what we saw in the iron germanium film. So we believe this is the indication of the dominant Hall effect. Dominant as compared to a anomalous Hall or ordinary Hall. When you keep going up the temperature, of course, we approach TC, and then this is keep shrinking, but still you have this Hall behavior. Well, this is the further zoom in, so you see that the coercivity is about 200 some Gauss. If you compare this with the iron germanium film, I just showed you a few slides ago, it has generally similar behavior. Okay, so going down here as compared to that. So now I want to compare this system with what Okura's group reported. I mean, these are supposed to be pretty similar systems, maybe the thickness is a little different, and technique of synthesis are different. They use BLD, we use sputtering. The loop shape looks seemingly different, but qualitatively, they are the same. Let me explain this. So, this is in their paper. They show the contribution to this Hall effect. The yellow or brownish dot is the contribution of the normal Hall, and this blue region is the topological Hall. So when they overlap these two, you get something like this. Or in our system, somehow the Skyrmion phase, or indicated by the topological effect, can exist with saturation here, just like our iron germanium. So this one dominates the normal Hall. So that's why we see this. Well, in the first paper, it's slightly different behavior, but it both shows the topological Hall resistivity. So this is very good data, right? So my students show this, you can see this is still not polished. We want to study a single layer. Okay, so before I showed this SRO, SIO pilot, which we believe is needed because SIO is trying to even provide the washcloth, the high spin Horn coupling. However, we just made one single layer of strong glutamate of 6 unit cell, which is 2.4 nanometer. We saw this typical autoclaving magnetization behavior, but then at close to 100 Kelvin, we saw the same thing. It reverses before it reaches 0. So even for a single layer of strong glutamate, we believe we still see the topological contribution. Although the mechanism we still don't quite understand, could be the top interface with air or the bottom interface, so we're going to have more measurement of this. So where may we go from here? So strong glutamate is a low temperature ferromagnet, but we do have the candidates that for the high temperature ferromagnet outside. For example, LSMO, lanthanum strong magnet. The bulk pure temperature is 360, and then we also have quite a few materials we study of magnetic double perovskite. The purity temperature can be up to 600 Kelvin. So those are the promising materials that we are going to study. But also in the oxide system, it offers the opportunity to tune the magnetic anisotropy by epitaxial strength, more so than the metallic system. So we know from the talks in the morning that the anisotropy actually played a very important role in the Skyrmion formation. So the goal is to get room temperature Skyrmions, but at a very small size, 10 nanometer or smaller. So here's the summary. So most I talk about the interface iron germanium film, mostly using the topological Hall effect to study the Skyrmions. But also I showed you our very recent results about the oxide bilayer system with Skyrmion formation. Thank you.
Do you observe any finite magnetization in the iron germanium? Would you expect the Skyrmion mass to be at 0?
Sorry, observe what?
With 0 field, do you observe a finite magnetization?
It's basically 0. I think we saw this magnetic history system. So this is the history system, and this small element we believe could be due to the a little bit of tilting. So in principle, it's a 0 magnetization at 0 field.
Are you expecting these things to be fully crystalline or singles?
Which one? The iron germanium? We believe the single with this epitaxial we have the XRT and TM.
So all films are the single chirality tonight.
That one I cannot answer because we could have 20, so that depends on, I mean, we can still have some defect. That I cannot say for
I
sure.
suppose my question is, are you expecting the receiver to left and right hand domain, or are you expecting a single Skyrmion domain across the whole sample?
I'm not sure how to answer that. Yeah, I cannot say that for sure. It's a single crystalline, but this chirality issue, like if you have one little change, I mean one defect, it could change the chirality.
So could you use the microism or your entity and the quality of these things? Some way of seeing Skyrmions directly rather than...
There are some Lawrence TM from our team that indeed show some white and white. So yes, so there are some chirality in both chiralities. But for this system, we haven't done the plan view. So those are the thick ones. We look at the side view, so it could be different. The preparation for this for the plan view is challenging.
Coming back to this constant iridium, constant interface system, the expected Skyrmion size is about 10 nanometers.
So that's what the Kura's calculation shows.
This is, of course, in principle, too small to see by Lorentz microscopy.
Right.
I'm wondering whether you have looked anyway at it by Lorentz microscopy to your system.
Well, there is Lorentz microscopy, the TN, but there's some other technique like what's under development. It's called a differential phase contrast loop. Potentially, then we also have a young TM expert, young faculty who's trying to do the atomic imaging, but hopefully we can resolve smaller than that. Or
Let me ask the question in a different way. The small Skyrmion size hinges on the large, extraordinarily large DFI value of the system.
Yeah.
Have you measured this DFI value independently?
We have not, but this is something we definitely will go into.
Do you have an explanation as to why you observe such a large topological Hall effect?
Not such a large topological effect. I don't have a sure answer. For example, the E20 phase, iron germanium, before our work, there's like the Hopkins work with, so it's much larger than manganese silicide. Manganese silicide should have like 3 nanometer, so something a few nanometer size. In principle, it should have a higher topological, but it has much lower. So I guess in addition to the Skyrmion size on the topological, there must be some other things that I don't understand. So iron germanium empirically has the largest topological. Until this strong loosening from the unit, the curve will observe something like half a micro ohm centimeter. We saw something similar, slightly larger. So it depends on a lot of mature parameters that we so far we can understand. I don't know whether the theory models can give some insight into that in the future. Yeah, so I don't know.
Okay, so if that's, oh, one last question.
So characterize all individuals direct.
No, we have, so these are neutrons. I don't know, I'm not expert on this neutron scattering, so it will be something to consider, but okay.
We are managed to see many structures, but actually we did not see students who actually that's why the PhD is worth it.
Okay.
So that's our last comment. The alternative might be small number X-ray scattering. Because if you can get the Skyrmion down to 10 nanometers, actually that means that they're at quite large angles.
Okay, so we really would like to have this, but these have to be grown on supergrid substrate, like some of the metallics we can grow on silicon nitride membrane. So sample prep. So we're trying to thin it down for TN, for X-ray, for many other techniques. But if you can make that sample, then those would be very interesting technique to look at.
Okay, so let's thank Fengyuan and so the next speaker is Jiarong Zhang from the University of Epitaxial.